So
Okay.
welcome everybody. My name is Rasmus Bro from University of Copenhagen in Denmark, and we are very lucky today because we have Alejandro Olivieri, who has been working for many, many years on especially second order calibration. He is kind of the king of second order calibration, but he has also done a lot of work on figures of merit in general, and that is what he's going to talk about here. And with that, please go ahead, Alejandro.
Okay, thank you, Rasmus. I guess you're seeing the picture, the introducing picture now, right? And the
Yes.
the pointer. Okay. This webinar will be on analytical figures of merit and uncertainty propagation, especially in multivariate and multiway calibration. And first question I have is, why do we need these figures of merit? They're just parameters condensing the properties of large data sets into a few indicators. And the best answer is that they are used for making fair comparisons. You know that today there is information, lots of information on football players, well, soccer in the US, but football for most of us, I think. And they have huge data sets. For instance, this picture was taken from an article from some years ago entitled Messi is Unique. And we see here a linear regression for hundreds of football players of goals scored against shot attempts. And here is Messi as a clear outlier in this linear regression. There were many pictures like this one in this article. This is another one, through ball assist against through ball attempts. Again, Messi clearly different from hundreds and hundreds of other football players. You know that they use the same techniques we use in chemometrics. We call it football metrics or soccer metrics in the US. There are many web pages where they explain how to use our same techniques on sports, especially on soccer or football. They even do some things like this one, talent identification in soccer using support vector machines, or even better, predicting sport results with AI. So if you want to know who will win the next World Cup football, you can ask these people or use their methods to see that. And now going to analytical chemistry, we are interested in a number of figures of merit, and one of them is the sensitivity. Sensitivity is defined in the same way as in real life, as the ratio of response to stimulus. And in the univariate calibration, it is relatively easy because the UPAC has already defined sensitivity as the change in signal for a change in concentration, where the signal is the response and the concentration is the stimulus. And this is easily defined as the slope of the univariate calibration line, as we know from basic classical analytical chemistry. Now, when we go to multivariate calibration, we can't apply this slope definition of the sensitivity because the signal is no longer due to a single analyte, it's due to a number of components. So we need an alternative approach, and this is based on uncertainty propagation. We add some noise to the signal of the sample with a standard deviation sigma x, and assuming that the noise is identically and independently distributed, the IID noise, we send this noisy signal to the model, assuming that the model is perfect, that it has no uncertainty, and we study how this noise is propagated to the estimated analyte concentration, and then we define the sensitivity as the ratio between uncertainty in signal to uncertainty in concentration. And this has allowed us to define a general expression for the sensitivity as the inverse of an effective regression vector, the norm of the effective regression vector, where this effective regression vector is given as the product of three important factors. One is a vector which allows one to select the analyte from the sample components. Then we have a matrix of profiles coming from the calibration phase. And the third factor, which is the one providing the second order advantage and depends on the profiles for the so-called unexpected components, those who are which are present in the test sample but are absent in the calibration. And this factor reminds the orthogonal projection of the signal to the space of the unexpected components. So when we go to PLS calibration, classical multivariate PLS calibration, we don't have unexpected components because PLS doesn't support the presence of unknown components in the test samples. The calibration matrix is equal to the matrix of PLS loadings, and the G vector is simply the latent regression vector of PLS. This equation has been known for a number of years, and there is much information about that in this classical paper by Faber and Kowalski. When we go to multiway calibration, for example, with Parafac, we have a matrix of unexpected components because we can resolve all components, even if they are not in the calibration set. This is the expression for second order analysis. There is an analogous one for third order, fourth order, etc. It depends on the profiles in the different instrumental modes for the compounds which are not in the calibration phase. Then we have the matrix of calibration profiles. These are the profiles of the instrumental signals for the components present in the calibration set. And then we have a G vector, which depends on a delta vector having a 1 at the position of the analyte and zeros otherwise. The other important model for multiway calibration is MCR-ALS. Here we also have an unexpected matrix of profiles for the components absent in the calibration, which it is equal to the spectral matrix, or in general to the matrix of these components in the so-called non-augmented mode. Then we have the calibration profiles matrix, which is equal to the spectra in the same mode, and a G vector, which again depends on a delta vector with a 1 at the position of the analyte. Then we also have N-way PLS, which has the second order advantage if you add a residual bilinearization procedure. Here we have the form of the unexpected profile matrix, which is the same as in Parafac. This the form of the calibration profile matrix, and G is again the vector of latent regression vectors in N-way PLS. We were interested recently in how to develop closed form expressions for the sensitivity in nonlinear models, going to the simplest one to the most complex one, kernel PLS, radial basis functions, multilayer neural networks, and convolutional neural networks. We have managed to develop expressions in all these 4 different nonlinear models. Here is the one for KPLS. This was for radial basis functions. Then we moved to the multilayer perceptron neural networks, and recently, in collaboration with Hadi Parastar in Iran, with a model for convolutional neural networks. The difference between linear and nonlinear sensitivities is that in the nonlinear models, the sensitivity depends on the sample, which is logical because the slopes are specific for each sample and depend on the concentration. This happens with all nonlinear methods. So you can't report a single sensitivity value, but you can report the maximum a minimum and an average sensitivity for your calibration samples. And what is interesting here is that the sensitivity is given again by the inverse of the norm of the vector, which we call it B, but this B vector is not a regression vector, it's a sensitivity vector. It's a vector with as many elements as spectra, but it is not used for regression, it's used just for defining the sensitivity. And these are the expressions for the elements of this B vector, which is used to calculate the sensitivity. It goes more complex as we go from kernel PLS to more complex neural networks, to a point that you no longer can form a closed form expression for the sensitivity, and you need to calculate the derivatives in a numerical way. This was done by Hadi Parastar, sorry, and for our joint paper on CNN networks. And we need the derivatives because the concentration is depending on the signal for the test samples. And when it is linear, when the model is linear, the derivative is simply the regression vector. And when it is nonlinear, we use the derivative for compute the sensitivity B vector. And of course, the expression is always the same. It is also interesting that when the model is nonlinear and you have a B vector for each sample, for instance, estimated by kernel PLS, you have a spread of B vectors, all different. They are specific for each sample. On the contrary, if the model is linear, then even if you use KPLS, but the problem is linear, you get the same B vector for all samples. So this is the basic difference between linear and nonlinear. And of course, there are intermediate cases. And we have proposed to use the spread of the B vectors to measure the degree of nonlinearity in the system and not to make a black and white division between linear and nonlinear. Now we use this sensitivity expression to study another interesting figure of merit, which is the prediction uncertainty, or the uncertainty in the estimated analyte concentration. We start with the general prediction expression in linear models. Analyte concentration is the product of the regression vector by the vector of the signals for the sample. And from this expression, in the simplest model, which is multilinear regression, or also called inverse least squares, the regression vector is simply given by the pseudo-inverse of the calibration matrix of signals by the vector of calibration concentrations. And from here, we can calculate the derivative of the predicted concentration, replace the derivative of the regression vector, and get a three-term expression, which shows from the start that the uncertainty in concentration is coming from three sources. The first one is the uncertainty in the signal for the test sample. The second one is the uncertainty in the signal for the calibration samples. And the third one is the uncertainty in the concentrations of the calibration samples. From here, we can replace this product by H, the vector, the leverage vector for the sample, and define the scalar H as the square norm of the vector H, and use it as a definition of the sample leverage, which we know it is a measure of the distance between one sample and the center of the calibration space. Here we see a distribution of many samples in a simple case where only two sensors or two variables define the position of the sample. And the red lines are the ISO leverage lines. Lines where all samples have the same leverage. and the leverage increases from the center to the outer border of the calibration space. So H is a good measure of the distance to the center. Returning to our three-term expression, it is relatively easy to go from here to the variance in predicted concentration as a function of the norm of the regression vector and the norm of the leverage vector. And since we have used our uncertainty approach to sensitivity, if the model has no uncertainty, this is 0 and this is 0, we only get the first term, and so the variance in predicted concentration will be given by this simple expression, and this leads to define the sensitivity as the inverse of the regression vector. From this expression to this expression using the uncertainty propagation approach. And inserting the sensitivity and the scalar h in our three-term expression, we get the final equation for the uncertainty in the estimated analyte concentration as a function of sensitivity, leverage, and the three, well, two, because this in general they are equal, but we expect to be identical, and the uncertainty in calibration concentration. That was true for multiple linear regression, but what about PCR and PLS? Well, in this classical paper by Faber and Kowalski, they showed that the expression is the same, except that the second term is given as an approximation where the leverage is defined in terms of scores, calibration scores from either PCR or PLS, and test scores for the test sample, And the expression was validated by Monte Carlo approaches and noise addition calculation, and it seems to work okay, even if it is an approximation. This is the final expression for all multivariate first-order models, including PLS and PCR, where again we have three terms coming from test sample signals, calibration signals, and calibration concentrations. One question people always ask is how to estimate these important numbers, the uncertainty in signal and the uncertainty in calibration concentrations. And the answer is that in instrumental signals, you can make replicate spectra or replicate measurements of your instrumental method for typical samples. If the noise is IID, I mean, it has the same variance and no correlation, then you will get from a few typical samples measured by replicate a good estimate of the uncertainty in signal. For the concentrations, if you need a reference method to build the model, as is done regularly in PLS studies, then you can take the uncertainty in your reference method as the uncertainty in calibration concentrations. Or if you prepare your samples, then you should know or have an estimate, an approximation to the uncertainty in calibration concentration from your sample preparation procedure. Now, what happens if the noise is not IID? Then, in a general case, we don't have a single sigma x to characterize the noise. We need the error variance covariance matrix. This matrix has the variances at all wavelengths or sensors in the main diagonal and covariances in the off-diagonal elements, measuring the degree of correlation among each pair of sensors. This is a typical IID trace noise and how the matrix, the covariance matrix looks. It has all elements in the diagonal equal because the variance is the same at all sensors, and zeros in all the off-diagonal elements because there is no correlation. For a type of noise known as correlated, where there is correlation in a certain window, then you have a matrix that has a diagonal and some off-diagonal methods elements which are fading away when you go to longer distances, but all elements along the diagonal are the same. And for a type of proportional noise, where the noise is proportional to signal, you have a covariance matrix where zeros outside the diagonal and with the diagonal with different elements which are proportional to the signal. And in general, you may have a combination of all these noises. Now, what to do with our expressions when the noise is not IID? This is the IID expression. We call it model 1. When you have the same covariance matrix for all matrices, all samples, both test and calibration, and this is typical of correlated noise. I mean, if you only have correlated noise, then you simply insert the covariance matrix between the two regression vectors which are multiplied here and here. And this we call it model 2. And the worst case it's when you have different covariance matrices for different samples. So you need one covariant matrix for the test sample and one effective covariant matrix, which is a linear combination of the covariant matrices for all calibration samples. This is really tricky, and we call it model 3. This was published in collaboration with Peter Wenzel, of course, because he is the expert on noise. And we showed in this paper by simulations that with model 1, it is okay when the noise is IID, but when the noise is correlated, you need model 2 because model 1 is not working okay. And when the noise is proportional, you need model 3 because neither model 1 or model 2 can do the job. The different colors here are for noise added digitally to only concentrations, only calibration signals, only test signals, or on all elements at the same time. And now the important question is how to estimate the covariant matrix. One alternative is from replicate samples. This is good when you have correlated noise and when the noise structure is the same for all samples. Then you take some typical samples, make replicates, and use this method described by Peter in this paper to estimate the single covariant matrix for all your samples. But when you have the worst case, when all samples have different covariant matrix, then you may need to model the covariant matrix. Again, this is a paper by Peter, and he showed here that you can model the covariant matrix from a few samples and then extend this model to all of the samples. And so you don't need to make replicate measurements for each sample. So as a summary, we have the expression for multivariate PLS calibration, the most general one, regression vector here, and covariance matrix here, and effective covariant matrix here, the most general expression. When we go to multiway calibration, we have the same expression, except that the regression vector is replaced by the effective regression vector. You know that both in Parafab and MCR, we have an effective regression vector, which provides the second order advantage. And also for nonlinear method, whether KPLS, RBF, or another neural network calibration, you get the same expression, except that now the regression vector is replaced by the sensitivity B vector, which I explained before is not used for regression, is used for sensitivity calculation. But the expression should be the same for all linear, nonlinear, multivariate, and multiway calibrations. Now I want to discuss the introduction of the analytical sensitivity into this picture because we got the conclusion that the sensitivity is not really the best parameter for comparing analytical methods for two reasons. One, it depends on the type of measured signal. You can't compare an electrochemical method with a fluorescence method, for example, using the plane sensitivity. And two, even if the signal is of the same time, these sensitivity values are only valid when the noise is IID. And when the noise is not IID, then it is no longer valid, the comparison. And I'm showing it this why. I start with the sensitivity, the prediction uncertainty expression, and we expect that for most samples, when the leverage is small, we expect that the error is inversely proportional to the sensitivity. This is the expected regular outcome from a set of samples. But this is only true when the noise is IID. Here we have done some simulations with different noise levels, and we see that the error increases when the sensitivity decreases, which is the expected outcome. Here we have errors obtained from PCR, PLS, and maximum likelihood PCR, which is a method for accounting for noise which is not IID. And the red circles are for MLR. So what is important here is that the error increases when the sensitivity decreases, which is okay. But when the noise is correlated, what happens is strange, because the error first decreases and then increases. So this behavior is not what one expects from increasing the noise in these simulated systems. So we proposed an extension of this old, rather old, 1970 definition of gamma, the analytical sensitivity, which is defined in univariate calibration as the ratio of sensitivity to noise in signal. And so we used our expression, take the first term and define gamma as the inverse of the square root of the first term, which translated to our simple propagation of uncertainty model means that we add some general noise to the sample signal, then use a perfect model to make predictions, and define gamma as the inverse of the uncertainty in estimated concentration after this non-IID noise is added. And we get this expression, which of course, when the noise is IID, goes to the classical analytical sensitivity definition. And with this definition, for all these both simulated and also experimental results, we get a nice trend of increasing prediction error for lower sensitivities. That's what we would expect for different models, different signals, and different noise levels. So we conclude that this general analytical sensitivity is better for methods and method comparison than the classical plain sensitivity. All this was published in 2016 in collaboration with this Brazilian researcher, Wallace Fragoso. Okay, because of lack of time, I have left some additional subjects. We don't have the time to discuss them here. One is the limit of detection in PLS calibration. We have shown that there is no single limit of detection. There is a range from a minimum to a maximum detection limit in PLS. And all you can do is to report this range, report the minimum and the maximum, and we have developed the expressions to estimate these two limits of detection. And the other subject I don't have to discuss is the rotational ambiguity uncertainty. Here, a different kind of uncertainty exists, different than the random noise and than the bias. It is a kind of a special uncertainty that it's due to the rotational ambiguity present in MCR calibration. And this is a field in itself. And I don't want to finish without saying some words about the R square, the determination coefficient or the correlation coefficient. You see that UPAC discourages the use of the correlation coefficient. According to UPAC, in this rather old paper, the correlation coefficient has no meaning in analytical calibration. In fact, I have received an email some time ago from a Spaniard researcher, and you see here, he wrote to me to seek support from colleagues who are determined to end the R-square era as a linearity criterion. And I would like you to join the group of researchers who believes that its application should finish. I responded to this researcher saying that I agreed with him, but it's difficult to struggle against the correlation coefficient because it is something which is, we have it in our blood. But it may be useful for other purposes. For instance, I am producing these T-shirts, which I expect to sell to analytical chemists and chemometricians. So the question is, why do you need the correlation coefficient? What is it useful for? And one possible answer is that it is useful to see whether there is a correlation between two variables in the case in which you don't expect a correlation or you don't know if there is a correlation. And we have here a nice correlation with a correlation coefficient of 0.791 between the number of Nobel Prizes per 10 million population against the chocolate consumption in kilograms per year per capita. And I have to add my country here because we have 5 Nobel Prizes, and I have learned from the internet that we are consuming about 2 kilograms per year of chocolate. For Rasmus information, Denmark is here. This picture is rather old. It's from 2012, I think. But there is an update from 2020. And this German researcher has updated the plot and found that there is still a nice correlation between chocolate consumption and Nobel Prizes. But he says that there is no causal relationship, that there are some hidden variables or that the relation is just by chance. So you can speculate on what is the deep cause of this relationship and this correlation coefficient. But in any case, a good advice is to eat chocolate. Okay, there is a summary of all this and some other things I left because of lack of time in this, one of the last numbers of the Journal of Chemometric, which I was lucky that it was selected as a cover for this number in November of this year. And thank you very much for being present in this webinar. And this is a picture of the Paraná River taken from my city to the other side. There's pretty much nothing until 50 kilometers from here. There is another small city in the next province. And this is a large bridge joining our province, Santa Fe, with the neighboring province, Entre Rios. And it was taken from this side, which is my city, Rosario. So thanks again.